Welcome to Internet Enterprises, your worldwide high-speed connection purveyor. During your trip on what we call the web, you will encounter a few friendly helpers along the way. You might come across algorithm, who will ensure that all the videos you watch are to your interest. Or perhaps you will come across bot, who will analyze your shopping behavior and make sure you get the best prices. Or maybe you go to a website to open a complaint. Then there will be an automated customer service representative to help you to the right department and to deal with all your problems. This would be the way the internet would be introduced to you if it was all company controlled. But we have all seen suggestions for things we have never thought about just to increase watch time. We have all searched for something and then seen advertisements for the exact thing for weeks. Heck, you may have even seen plane ticket prices rise the second time you browse the same dates. This is all done because there are artificial intelligences, or AIs, keeping an eye on what you do online. No matter if we call them algorithms, bots, or automated systems, they are all AIs. Traditionally, we divide AI in two different segments. In the olden days, when the field of artificial intelligence started to emerge, the first approach was symbolic AI, or more commonly called good old-fashioned AI. In symbolic AI, all methods are based on symbolic representations of logic, most commonly a chain of if-and-then statements, ands, ors, and buts. This was great when all was simple, but many problems are too difficult to program in this way. When you want to tell an AI to check if a light is on and if it's on, press a button, that's simple. However, if you want to tell an AI to sort pictures of bats and cats, that's not that easy. Sure, the task of sorting bats and cats is simple for humans because we have words to tell ourselves how to differ between them, but to tell an AI in computer language what the difference is between cats and bats is near impossible. The way of building AIs had to change, and boy did it change. In the late 1980s, the majority of AI research shifted to the sort we use for the majority of projects today, statistical AI. Statistical AI uses sophisticated mathematical tools to streamline the development, allowing researchers to compare and unify the building blocks they used for their project. Because of the shared language that was found in mathematics, the field had a real boost to their productivity and effectivity. This new statistical learning was gaining traction and saw real-world use, such as with data mining without needing to fully understand the underlying sets of data, leading to a scientific boom. This might all sound new to you, but I'm sure you have heard of this by a different name: machine learning. Two popular methods in machine learning are artificial neural networks and evolutionary algorithms. Let's take a moment and do a deep dive into how artificial neural networks actually work. In artificial neural networks, computer scientists attempt to program what happens in our brains into an AI. To do this, the programmer starts by programming an artificial neuron. A neuron takes an input, either from an exterior source, such as an image, or from another neuron, and then uses a weighing function to attribute weight, a name for its importance, to the input. It then aggregates these values by adding them together while considering a bias value. The reason we have to add a bias value is because real-world problems often have an expected value. If we, for example, screen a group of high schoolers to find the best basketball players, we can offset the height value with a bias equal to the average height at a particular age. This allows for far more precision in our system, as we can even set the bias to be the average of all high schoolers. That way we can compensate for prior knowledge that this is a basketball team we are putting together, so the average height will probably be higher than normal to start with. This is then run through an activation function so that our output becomes meaningful to the AI instead of a potential unbounded giant number which our AI might have difficulty to interpret. Often you will see that a sigmoid function is used, a nice mathematical function that can be bounded and is shaped like an S. By bounding this between 0 and 1 in the case of the sigmoid function on the left, we can look at a single outcome question, such as a yes-no question. Or we can bound it between -1 and 1 in the case of the sigmoid function on the right, for a double outcome question, such as identifying bats from cats, where a 0 value means neither. We can then convert it back to probabilities, which are legible to the human operator, or have the AI make its own decisions. The value is then sent to other neurons, and the whole process starts over again with different weights and functions. Combining a handful or more of these neurons gives us a neural network, where each input can affect multiple of these mathematical blocks, which are called hidden layers. Not just that, the hidden layers can also affect other hidden layers, which can affect other hidden layers, leading to a very complex system. Now, let's build an AI that can actually sort pictures of bats from pictures of cats. Well, as we just discussed, this is a problem too difficult to fix with good old-fashioned AI. So instead we build two simpler AIs, a bot that builds bots, and a bot that tests bots. These are much simpler bots and can be built by a person with a high skill level in good old-fashioned AI. From here, we let the bots do the work. The builder bot will start building AIs, but at first the AIs it builds will be unreliable at best. BuilderBot has no idea how to build the neural networks in the AIs, so it simply decides to connect random wires, and hopefully one of these will be lucky. He then sends them off to TesterBot, who we have given a list of pictures of bats and cats and the answer key as to which one is a bat and which one is a cat. Then the newly built AIs will take the test, and despite doing terrible, they get sent back to BuilderBot. BuilderBot looks at the scores, keeps the best of the bunch and recycles the others. Now, BuilderBot makes some new AIs, tweaking a little randomly with the neural network inside their head. And off they go again to TesterBot. Get tested and rinse and repeat. At first these developments seem random, and whichever AI is the best cannot be predicted. But after iteration upon iteration of this, the AIs are no longer lucky, they are skillful. This doesn't mean they are perfect. Remember, for us humans it is easy to recognize a cat from a bat because, well, they are very different. For an AI, however, there are still some pictures that might confuse it a little. This is not a problem, because we are not doing this once, but hundreds of times per day. We're not building 3 AIs at a time, we are building thousands. And the test is not 10 questions long, but millions. Eventually there will be an AI that is genuinely able to differ between bats and cats. And he will be the reigning AI until one comes along that is just a fraction better. However, this leads us to a problem. The AI is now so developed that not the human nor the bots that build it fully understand what is going on in the network. Because much like in neuroscience, a neuron may be understood, a cluster of neurons function grasped, the whole brain is far too complex to comprehend. So too can a single node be understood, the function of a group of nodes grasped, but the whole network is far too complex to comprehend. This is called the explainability problem, and it is a struggle of function and form within the AI development community. Nevertheless, this is how Uflix and Twixer keep you watching, FaceTwitIn suggests connections, and how stock markets buy and sell millions of stocks every hour. But all these AIs only have one function. They are all built to do just one thing. May it be sorting pictures, keeping your attention, or buying and selling stocks. What if there was one AI that could do all these things at the same time? And many more. What if there was an AI so good that it could do anything a human could, and you, dear viewer, couldn't tell if it was an AI or a human if you were communicating with it? More on that in part 2 of this series on artificial intelligence.